Hold an object closer than a few inches to your face, and the image immediately blurs. You've hit a physical wall in your own biology. Human size perception relies on the angle an object forms at the pupil, known as angular subtense. When an object moves closer, it occupies a larger angle in your field of view and appears larger to the brain. However, the eye can only focus within a specific range. The closest distance of distinct vision is called the near point, or D. For a normal eye, this value is approximately 25 centimeters. Moving an object closer than 25 centimeters increases the viewing angle, but it forces the ciliary muscles to strain past their limit. The lens cannot curve enough to focus the light, leaving a hazy projection on the retina. Most optical math relies on the small angle approximation. As the angle theta decreases, the vertical tangent and the arc length converge. In radians, we can assume the tangent of theta is equal to the angle itself. A convex lens serves as a geometric bypass. It allows the eye to capture widely divergent light rays from an object held extremely close while maintaining a sharp focus. The simplest version of this bypass is the single-lens simple microscope. Its function is to create a virtual image, an image where light rays only appear to originate, that is farther away than the actual object. In near-point adjustment, the object H is placed just inside the focal length, F. The diverging rays are traced backward to form a magnified virtual image. This image is projected exactly 25 centimeters away, landing precisely at the near point D for clear viewing. This setup yields a magnification of 1 plus D over F. The 1 represents the inherent angular size of the object if viewed at 25 centimeters without help, while the second term accounts for the lens's contribution. In normal adjustment, placing the object exactly at the focal point F makes the exiting rays perfectly parallel, projecting the virtual image to infinity. This allows the ciliary muscles to fully relax. The magnification becomes simply m equals d over f, permitting extended observation without eye strain. We measure the converging strength of these lenses as power, defined as the reciprocal of the focal length. The unit is the diopter, where 1 diopter equals 1 over a focal length of 1 meter. Even in a relaxed state, the simple microscope provides magnification because it allows the object to sit at the focal point, while the eye perceives it as if it were 25 centimeters away. If shortening the focal length increases power, we should theoretically be able to achieve any magnification with a single lens. But physical glass has limits. Highly curved lenses suffer from spherical aberration. Light hitting the edges of the lens bends at a different angle than light hitting the center, preventing a single sharp focal point. Thick lenses also cause chromatic aberration. Because different colors of light refract at different angles, the lens acts like a prism, splitting white light into a blurred rainbow of colors. These distortions make single lenses largely unusable for magnification greater than about 9 times. The solution is the compound microscope. It splits the work into 2 stages, a linear projection followed by an angular expansion. The first stage uses the objective lens, the high-power element located closest to the specimen. The specimen sits just outside the objective's focal point, FO. The lens projects a real, inverted image, H', deep into the tube. The distance between the objective's second focal point and the eyepiece's first focal point is the tube length, L. The objective provides a linear magnification equal to the tube length divided by its focal length. MO equals L over FO. Here, the objective acts as a projector, scaling light rays into a real image for secondary processing. To calculate this, we use the Cartesian sign convention. Distances in the direction of light travel are positive, while inverted images are assigned negative values. The objective lens has successfully cast a magnified ghost of the object into the tube. The second lens, the eyepiece, now treats that floating intermediate image as its own object. The intermediate image is positioned exactly at the focal point of the eyepiece, FE. The eyepiece functions as a simple microscope, taking the objective's projection and expanding its viewing angle for the eye. The magnification for the second stage is D divided by FE. The eyepiece is the final gateway, formatting stretched light from the objective for the human retina. The total magnification equals L over FL multiplied by D over FE. With both focal lengths in the denominator, smaller values create massive magnifying power. This is the inverse of a telescope's geometry. A telescope uses a large objective focal length to view distant objects, while a microscope uses a tiny focal length to resolve small, nearby ones. The compound microscope is a multiplier for optical laws, bypassing the physical distortions of individual lenses. Vision measures the angular space light occupies on the retina. Optical instruments act as tools for angular expansion, designed to stretch that perceived space. Yet even with complex arrays of mirrors and glass, the final instrument in the chain remains the human eye and its 25-centimeter limit. Mastering the geometry of refraction bypasses our physical constraints, rendering visible the cellular structures hidden in a single drop of water.